Hello, in this lecture presented by www.free-academy.com, we're going to be doing a problem one of our users have submitted to the website. And this person is asking if we're given the equation f of x equals x to the third minus 3x squared plus 3x plus 1, find the intervals where it's increasing and decreasing and where it's concave up, concave down, find the relative extrema, inflection points, and sketch out the graph. So that may be a bit of a mouthful, but the process is actually fairly straightforward. We're going to need the first and the second derivatives. So we'll start out by finding the first derivative is equal to 3x squared minus 6x plus 3. And the second derivative is going to be equal to 6x minus 6. The next thing we need to do is we need to find where the first and second derivatives are both equal to 0. So 3x squared minus 6x plus 3 equals 0. The reason that we need to do this is because this is actually going to tell us where our critical points are. And once we find where the zeros are in the second derivatives, this is going to tell us inflection points and things of that nature. So in the equation 3x squared minus 6x plus 3, we can very easily divide out the 3, get x squared minus 2x plus 1. And this should be equal to x minus 1 and x minus 1 if you factor it. In which case we have an extrema at 1. So this will give us an interval. Okay. The next step after you find the zeros in your equation is you need to find your intervals. So you set up a table, negative infinity to positive 1, and then from 1 to positive infinity. And then we're going to pick a dummy point in these intervals, say like 0 and positive 2. And then we're going to put these numbers back into the equation here to determine if we get a positive or a negative. So 0 in x squared minus 2x plus 1 gives us positive 1. And 2 in this equation is going to give us 4 minus 4, positive 1. So this is plus 1, or this is positive again. Now if you recall back to the lecture on this, when we have a positive in the first derivative test, we have an increasing. So what we've determined so far on this graph is that we have a critical point that occurs at x equals 1, and the function is increasing before and after. So it may not seem like it's told us a whole lot yet, but let's do the second derivative test and find out about the concavity. Change my color here. So we have 6x minus 6 equals 0, and I think that should be pretty clear that occurs where x equals 1. Which makes perfect sense. We only had one critical point that occurred at x equals 1, so that needs to happen there too. So we set up our interval again, negative infinity to 1, and from 1 to positive infinity. And you take dummy numbers, just as long as they're less than 1 or greater than 1, and put them back into the equation and see what you get. And in this case, you get a negative for putting in 0. It's equal to negative 6, and if you put it in 2 you get positive 6, which is positive. So in our second derivative test, when we have a negative number, this is akin to concave down, and a positive number is equal to concave up. And I didn't go into any detail with this before, but in our first derivative test when we had a positive, that means that it's increasing. A positive means that it has a positive derivative, which means, it must be increasing. If it's negative, you have a negative derivative, that means it has to be decreasing. But what's going on here in the second derivative test is we're actually finding the rate of change of the derivative. So from negative infinity to 1, we have a function that's increasing, but the derivative is increasing less and less as you get there. And on the other side, it's increasing more and more. So let's bring up a piece of graph paper. And we know that this occurs at x equals 1. And so let's put 1 into f of x to see what that value is. That's equal to 1 to the third minus 3 times 1 squared plus 3 times 1 plus 1. These cancel, you get 2. So at 1, 2, we know that we're increasing over the whole interval, which let me take some white here. And then we also know that we have concave down before 1 and concave up after 1. So our function, if we're just going to do a really quick sketch of it, we got to cross this point here, would look something like this. It's increasing all the way across, but it's got a negative curvature, it's got a downwards curvature before 1 and it's got an upwards curvature after 1. And in fact, I've actually graphed this function going into this, and that's exactly what it shows. Now actually, let me give you a little bit more time to look at it. So we're increasing all the way across, but we have a negative curvature going in, positive going out. It's a critical point at x equals 1, but another thing that you should be more familiar with is in fact that this is equal to this is an inflection point. When you're going from negative curvature to positive curvature, you have an inflection point. So we've covered the extrema, we've covered the inflection points, and alright, so that answers the entire question there.